Good morning, dear students. Welcome to another session of microwave and antennas. So in previous session, we completed our discussion pertaining to short dipole and its associated field parameters, and we discussed field associated with the thin linear antenna. And we also looked into how we estimate the radiation resistance of a given antenna. So in previous session, we derived the radiation resistance for the short dipole or the Hertzian dipole. Now, in coming forth sessions, we'll start off our discussion with the loop antennas. Then, what is meant by horn antennas? What are the different types of horn antennas? Then, apart from that, this we'll be discussing regarding helical antenna. Then we'll be discussing regarding Yagi-Uda antenna and their applications, and few of the parameters which are associated with those antennas. So this is what we'll be discussing in the coming forth sessions. So in today's session, we start off our discussion with respect to loop antennas. So by definition, what we call an antenna to be a loop. So an antenna in which it forms a closed, say short circuit kind of structure, we call such kind of antennas as loop antenna. So for example, I am having a long wire. So this also can act as an antenna. This is say a linear kind of antenna, which is a wired antenna. Now, if this antenna, what I do is I create a loop out of this wire. I create a loop out of this wire. So, and I feed the input to this antenna, this say structure. And if it radiates, then what happens is such kind of structure in which it is forming a short circuit DC, a short circuit specification over here, such kind of antenna is called as a loop antenna. Now here the loop can be in any form. So here we have shown it as circular. So it can be circular in shape, the loop antenna. Then apart from that, it can be square. So this is also a loop which is in the square form. It can be in the rectangular form. It can be in the rectangular form. Apart from that, it can be say rhombic in structure. It can be rhombic. So this is also for forming a loop. So this loop is nothing but the short DC short circuit version of the wire. So this one we classify it as a loop antenna. So under this again we can have different parameters depending on what is the diameter or the specification which is associated with this. Say if it is circular, right? I look at the parameter that is the radius of this one. And if it is say square or rectangular, I look into the length and breadth details of these aspects. So if it is rhombic, I try to see what is the aspect related to these. So based on these specifications, right, we can have loops classified as small loops and large loops. So later we'll discuss regarding as to which one we call as small loop and which one we call as the the large loop. So basically it is relevant to the circumference which is associated. So that part also we'll be discussing, in which we have C by lambda. Based on this value, I classify the loop as small loop or large loop. So where C is the circumference. So if I take the circle, right, if the loop is in circular in nature, if I take the circumference, its circumference, if the radius is say A, if the radius is A, then its circumference is 2 pi A. So this is the circumference. Similarly, I need to estimate the circumference of, say if it in whatever shape it is there, I need to first estimate the circumference. And what is the operating wavelength associated with this circular or with this loop. So based on that, what we do is if C by lambda is very much lesser than phi, if this is the condition which is happening with association with the circumference of the loop antenna and the operating wavelength, then I classify the antenna as, or the loop antenna as, a small loop case. Or else, if this condition is not satisfied, that is c by lambda is greater than equal to phi. If this is the case, then the loop is termed as the large loop. So this is the condition based on which we do the classification. So again, I just repeat it. If c by lambda is much lesser than phi, so this will be a small loop antenna case. And if c by lambda is greater than or equal to phi, then this one is the large loop condition. So now in this case, we'll just consider the small loop at the starting. So here we can observe that we have a structure which is circular in shape. This same structure can be represented as a square over here. Now, if I just consider the radius of this circle is a, then and if I assume that the length of one side of this square is d, then what happens is area of this square loop is d square, whereas area of this one is pi a square. Now, when we consider this loop structure, I can create the loop either in this form or in this form. So in this case, what I can write is I can write the area which is covered by these two is equal. Therefore, I can write d square is equal to pi a square. D square is equal to pi a square. This will be useful when we are going further with some derivations. For that part, we are discussing this case. So here we are considering a loop, and we can have the loop in circular form, which is having an area of pi a square, and the same area can be obtained by creating a loop which is having the one side length equal to d, and the area of this one is equal to d square. Now, since I'm using this, I can equate the area of these two as equal. So this will be utilized in the coming fourth derivations. So this is pertaining to a small loop. So what is small loop? Again, I specified where c by lambda is much lesser than phi. So this is the assumption what we are considering. And now, when we are doing the analysis, right, we can consider either of these two. So in this case, first we'll consider this one and see how it appears. So I want to do some analysis pertaining to this. Then how do I go ahead? So if I consider the loop, how it is associated with the coordinate system. So again, I'll be making use of the spherical coordinate system. So here I place the square loop structure as shown in this figure. It is placed as shown in this figure. So wherein the center of the square loop is the center of the coordinate system. Now what we do is at a distance point P, which is having the coordinates r, theta, phi, which is having the coordinates r, theta, phi, we try to estimate what all field parameters are present. So what are the parameters associated with electric field and what are the parameters associated with the magnetic field? So we try to estimate those. And this is the orientation what we are considering. So we are considering that the loop is placed along XY plane. It is placed along the XY plane. So this is the orientation what we will be looking forward. So when we are having this orientation, that is the square loop, if it is placed in the XY plane such that Z axis is perpendicular to this XY plane, that is to this loop, and at an angle of theta and at an angle of phi, which gives me the point P, we try to see what is the field parameters. So again, we can go for either near field parameters or far field parameters. Generally, we prefer for far field parameters for the radiation. Now, what we do is, if you just observe, if you pass the current through the loop, it will enter from one direction and it continues. So here we can see that the direction still continues for the current and it moves further. So because of which we can have an associated magnetic and electric field because of the current which is flowing through the conductor. So now in this process, if you just observe, if I consider two opposite wires over here, so one is this side and the other one is the other side. So if I just analyze what is the field due to these two elements, I'll be able to estimate the overall total power radiated by this loop antenna. So now what we do is we slice this XY plane. We slice this. So when we slice it, so we have these two, that is, this is represented with 2 and this is represented with 4. So this is 2 and 4. When we slice this, what happens is I'll be able to observe only the diameter of this wire. I'll be able to obtain or observe only the diameter of this wire. So here also it will be the same thing. So now what we do is we consider that analysis. So this is the sliced version or the cross section, what we specify. So that is, we have taken this and we have taken the cross section along the YZ plane, along the YZ plane. So when we consider that, so we can look at this system as, when we are slicing it, I'll see 1 point over here and 1 point over here. This will be like a dipole. I can observe it as a dipole. And due to this dipole, what is the field? Then what I do is I sum up all the values which are associated with that and obtain the overall electric and magnetic field. So when I'm slicing, I'm able to see this cross-sectional point. So that is what is displayed over here. So now what we can consider is, we can consider it as a dipole system. Now in this case, if I just see, these are the conditions what we had discussed in the previous sessions. That is, two array of two isotropic point sources. So it is like array of two isotropic point sources. But now instead of isotropic, we are looking for the dipole sources. That is, the antennas which are under consideration are the dipoles. Now, what happens is, why we have a cross and a dot, if you just observe what is happening over here in 2, current is flowing in this direction. Say that is, it is flowing into the book, and this side, if you just observe, it is flowing in the opposite as compared to this element 2. So they are both opposite to each other. This is flowing out of the book. So that is what is represented over here. So this is like, you might have in previous this thing, right? We had observed, we had a dipole system wherein plus and minus is present, and due to which when the charges are exchanged with each other, we observe that the fields get radiated. So that is what is happening in this case. So it is basically telling, in you are moving into, that is in one direction. So in the say, I'll specify it as the negative Z direction, and this one as the negative X direction, and this one as the positive X direction. So because of that, you have representing one dipole with a cross mark and one dipole with a dot. So this is like a array of two sources, and the sources are dipole. So this is how it can be represented. Now considering this system, right? Considering this system, we try to observe at a distant point what is the total field due to this entire structure, due to this condition. Now here, since we are doing that, we are considering the elevation angle. We are considering the elevation angle, whereas in previous cases, what we had done, we had considered the azimuth angle and we had done the derivation. So now because of the orientation what we have placed over there. So now we consider the at an angle theta and at a distance point, what is the total field? So we need to estimate this. So this already we have done it by considering the isotropic point sources. We have done it by considering the isotropic point sources. So, but what is the minor change over here is you have to consider the theta parameter, and apart from that, you can see that one is the direction of the current what you observe. In this, it is opposite to consider to the dipole 2. So because of which what happens is the electric fields associated with both are in phase quadrature. So now what happens is based on that, we can estimate what are the components associated with electric and magnetic field. Now when we are considering the far field components for this loop structure, right? We have two components in the far field. One is E phi component and another one is H theta component. It is based on the orientation what we are talking of. So based on that, what we can specify is we can have the total field E phi. The total field E phi will be the vector addition of field due to one of the dipoles, say dipole 2, and the field due to the other dipole, that is dipole 4. That is, one field is associated with this and another field is associated with this. Therefore, the total electric field at this point will be the addition of field due to dipole 2 and field due to dipole 4. So that is what we are looking forward. So therefore, it will be given by this equation. But why is this minus sign put over here? It is because we observed that the current what is flowing, because of this, what happens is the fields will be opposite to each other. So here the direction is in this way, but in this case, the direction is opposite, because of which that minus sign is included. So therefore, the total field in the phi direction will be given by minus of E phi naught e raised to j psi by 2 plus E phi naught e raised to minus j psi by 2, where E phi naught, this parameter, is the electric field with respect to the individual dipole. It is with respect to the individual dipole. And what is the parameter psi? It gives you the phase information, which is again beta times dr, which is beta times dr. And in this case, when I estimate dr, right, it is equal to d sine theta. It is equal to d sine theta. So based on that, what we have, psi is equal to beta times d sine theta, where beta is nothing but 2 pi by lambda. So 2 pi by lambda into d sine theta. So this is the parameter which gives you the phase information associated with those field values. So now when I simplify this parameter, I multiply this one with 2j and divide by 2j. Considering this, I multiply and divide by 2j. So what happens is I'll be having minus of 2j into E phi naught. This is anyways common, so you can remove it common. And the remaining parameter what we'll be having will be nothing but sine of psi by 2. It will be sine of psi by 2. So this is, after you simplify this equation, we will be having the total field, which will be represented by equation 4, which is E phi, which is equal to minus 2j times E phi naught sine psi by 2, where psi is equal to what? Dr sine theta. So it will be dr sine theta by 2. Now what is j implying? It is implying that the total field is in phase quadrature with respect to this field parameter, which is due to the individual dipoles. That is the electric field due to the individual dipoles. The total field is in phase quadrature. So now when we consider that the d value is very much lesser than lambda, then in that case, what happens is, so D parameter, what we are considering. So in that case, what happens is this value, what is there? If D is very much less than lambda, then what happens is here we can observe in the overall equation, dr by 2 will be very much lesser than, that is dr by 2 sine theta will be very much lesser than 1. It will be very small. So therefore what happens is this sine parameter will be nearly equal to dr by 2 sine theta. So because of that, what happens is we simplify this equation. When we simplify this equation using the concept that sine x, that is sine x is nearly equal to when x is very small, when x is very small. So in that case, what happens is we apply that concept over here and simplify. When we simplify that, what we have total field given by minus j e phi naught dr sine theta. So this is the field which is associated with this structure. So now, once we have obtained the electric field, we can obtain the magnetic field. Now, previously we had seen that what is the field which is obtained due to a dipole. So in previous session we had obtained due to a dipole what is the electric and magnetic field. So we consider those equations over here, and we can substitute that in this parameter. So in this case, we can observe that E phi naught is given as J times 60 pi. This is the retarded current. This is the retarded current into L. L is the length of the dipole divided by R into lambda, where R is the distance from the origin of the dipole, distance from the reference point of the dipole to the observation point. So this is the equation what we had obtained previously. So referring to this equation, when we substitute equation 6 in equation 5, so what happens is j into j, when it comes, it will be equal to j square, which is equal to minus 1. So minus of minus gets cancelled. So therefore what happens is when I simplify it, I end up with total field which is given by this equation, which is 60 times pi into the retarded current into L divided by R lambda into dr sine theta. So this is the electric field which is associated with the small loop what we are discussing. So now what happens is if we consider the where in this case we have the length L of the short dipole is same as that of the D value what we are considering. So if this is the case, that is D is the distance between the two dipoles. D is the distance between the two dipoles. So if you look at the structure right here, so if one side, if it is a square loop, if one side is having a length of D, this side is also having the length of D. So if you just observe, the distance between these two is also D. The distance between these two is also D. Now if you just observe this one, so this is a dipole what we are considering. This is a dipole what we are considering. So when we consider that, what happens is, what is the length of this dipole? Length of the dipole is equal to the length of the side of the loop. So therefore L is equal to D. So because of that, we have this case, that is L equal to D. The length of the dipole is equal to the side length of the loop. So because of which we can just consider, we can replace L in this D parameter. That is, this is beta times d2 pi by lambda into D. We can replace it as 2 pi by lambda into L. So at present we'll not disturb that. So we'll continue with the same this thing. So now what is the area of the loop? So area of the loop is equal to D square. since it is a square loop what we are considering, and whose side length is d, therefore area of the loop is equal to d square. So when we consider this equation turns out to be E phi, which is equal to 120 pi square retarded current into sine theta divided by r into a by lambda square. So this is all after substituting these values. After we substitute these values, considering replacing the parameter d over there. So this is what we will be getting for the small loop. So once we obtain this parameter, what we can do is we can obtain the other field parameter, which is the magnetic field. And we had seen that, say in this case, we have E phi component and H theta component in the far field. So we can equate this to what? 120 ohm, which is the intrinsic impedance of the free space. Therefore, what we have H theta is equal to, it is equal to E phi divided by 120 pi. So that is what is given over here. So now when I substitute E phi from the previous equation and simplify it, this is the overall result what I'll be getting, which is equal to pi into retarded current into sine theta divided by r into a by lambda square, where a is the area of the loop what you are considering, and lambda is the operating wavelength on which the antenna is operating or the loop is operating. So this is the field components associated with the small loop. Next, actually, we have still further discussion in which we'll be considering the loop in a general case. The loop in a general case. So this is for the small loop field parameters what we have discussed. Now let us just have a comparison of the fields which are associated with the small loop and the short dipole. So it is again, these parameters are again associated with the field values what we had obtained for short dipole, but we have to consider the orientation. So based on that orientation, we have these field values for the short dipole or the Hertzian dipole, which is given by we have E theta and H phi components, which is given by this equation, that is J times 60 pi into retarded current into length of the dipole into sine theta divided by r lambda. And we have H phi component, which is given by J into retarded current into length of the dipole into sine theta divided by 2 times r lambda. And now we obtained for the small loop. So in this, these are the values what we have obtained. So in this case, one parameter you can just observe. Here for the same kind of orientation, we have field component which is equal to E phi, that is in phi direction I have the field component, electric field component, and in theta direction I have the magnetic field component. So what does this imply? It implies that the other parameters, that is in this case it is the radial component of electric field, the theta component of electric field, then the radial component of the magnetic field, and the phi component of the magnetic field. All these are zero. All these are zero. We have only these two components which are present. So what is this specifying? It is 120 pi square into retarded current sine theta divided by r. And here it is given as a by lambda square, where a is the area associated with the loop. And if we divide this one by 120 pi, we obtain the value for h theta. We obtain the value for h theta. So this is what we obtain for the field values associated with the electric dipole, that is a short electric dipole, and the small loop antenna. So next we have loop antenna, the general case. So previously we considered a small loop and we discussed that. Next we discuss a general case associated with the loop antenna. So in this one, we say consider a circular loop And we try to see due to this circular loop at a given point P, which is given by r theta phi, what is the field associated with this, and what is the using that field I try to estimate what is the overall total field which is presented by the loop what we are observing. So in this case, again, what we do is we assume that we place the loop in the xy plane. So we are placing it in the xy plane such that the center of the loop is the center of this xy plane. That is the origin of this coordinate system. And z-axis, if you observe, it is perpendicular to this loop, to the plane of the loop. Now what we do is from this reference point, if we traverse a distance of r and we consider an observation point, so at this observation point, what is the total field? What is the field due to this loop? So we need to identify that. So in order to do that, what we do is we again convert this entire system into a system of dipole, and then we apply the same conditions and obtain the field parameters. So now let us see what parameters we can consider over here. So again, I'm just specifying we are considering a point P which is at a distance r from this origin, and it is at a and it is having an elevation angle of theta, and it is having a angle of phi. It is having an angle of phi, that is the azimuth angle. So based on these all specifications, we have to look forward with what is the orientation associated with, and from that we try to observe what is the field which is associated. Now when we are considering this, what we do is we consider a small elemental length on the loop. So we consider this loop, we consider a small elemental length. So from origin, I consider a small elemental length. Now, if I consider that A is the radius of the circle of this loop, then here, if I consider that, this is an angle of d phi. That is, it is placed in the xy plane. Based on that, this is the phi direction what I am having. So what I am doing is I'm just considering a small elemental angle which gives rise to a small elemental length of this loop. So what is the length of the small elemental parameter over here? It is nothing but it is given by radius into the angle. So if you remember, you have this equation, right? If this is the length of, if the two sides length is L and this is theta, the length of this parameter is given by L theta. It is given by L theta. So we have the length of this one is given by L into theta. So we consider this as this thing, and we try to do the analysis. So what we do is we consider one side of this and the opposite side of the same. So when we consider this is also having A into d phi. So considering these two elements, we try to make the analysis. So what we are doing is we are considering one side of the element and the other side of the element, and then we are trying to do the analysis. So it is like this is one dipole and this is other dipole whose length is given by A into d phi. A into d phi. The length of, we are considering two dipoles. So when we slice off, we consider a small element, so whose length is A into d phi and A into d phi. So considering that, we apply the previous concepts what we have discussed. So based on that, we look forward with the derivation. And in order to refer to this, we again make use of the vector retarded potential. We make use of vector retarded potential. So these are the considerations what we have to look forward in this derivation. So now, say because of the placement of the loop in the xy plane, what happens is we have only the phi component which is associated with the vector retarded potential. So what is that? Now here we what we did, we consider a small say in this case what we are doing, we are considering a small elemental value, so whose length is a into d phi. And since this entire structure is placed along the xy plane, what happens is we have the vector retarded potential. I'm not considering the area at present. It is the vector retarded potential, which will be having only the phi component. Now, since we are considering a small elemental value, right, what happens is this will be a elemental, it will be the elemental vector retarded potential. It will be elemental vector retarded potential. So therefore, when we consider this orientation along the xy plane, when we consider this, we have only an elemental value along the phi direction for the retarded potential, and A represents the vector retarded potential. So therefore, what happens is we have d a theta and dA are 0. Therefore, as per the equations, what we have is we have the elemental retarded vector potential given by mu divided by 4 pi into dm. So this equation is again derived from the previous discussions what we had, wherein we observed that starting with az we obtain the retarded potential, then we obtain the retarded potential, scalar retarded potential, and then using these two we obtained electric and magnetic fields. So it is all relevant to those parameters. So now we are considering those equations directly over here. So therefore we have elemental vector potential, which is given by mu by 4 pi r into dm. Now what is dm in this case? It is the current moment which is due to the one pair of element which is shown. So here what we have, so here we had considered elemental parameter, right? So that is a into d phi, the current moment because of these two elements. So on the circular loop, you had considered the elemental parameters. So one element is a d phi and the other element is a d phi. The current moment because of these two, is represented with dm. So that is what is represented over here. Now, when we consider the phi potential, phi component, right, of the vector retarded potential, so associated with that, what we have is the current moment is given as the retarded current into a d phi into cos phi. It is retarded current into a d phi into cos phi, which is the phi component associated with the retarded current moment. So this is the retarded current. Now this gives rise to a retarded moment, so which is given by this equation, and this one is the elemental length what we are considering for that loop. So now based on this, as previously we had seen, the retarded current is given by, this is the peak value of the current. Say we sometimes we represent it as Imax or sometimes we represent it as I naught. So which is I into e raised to j omega t minus r by c. So this is the retarded parameter what we need to consider. And this one is not bracket, so it is actually just I, where I in this case is the peak value of the current. Now, based on these parameters, we can have dm, which is given by equation phi. dm, which is given by this equation, which is 2 times j into retarded current into a d phi cos phi into sine psi by 2. So now based on these specifications, we look forward for obtaining the potential. So now in this case, what happens is psi parameter for the given orientation and given loop condition, it is given by 2 times beta a cos phi into sine theta. So this is the phase what we'll be looking out when we are considering those small elemental values. So psi is given by 2 times beta a cos phi sine theta. So now when we substitute these parameters in dm, right, we obtain equation 7. We obtain equation 7. Now here we can see that d of a phi, we obtained what is the value of dm. Now in order to obtain the phi component of a phi, we need to integrate this entire equation. We need to integrate it with respect to what? With respect to the phi component. We need to integrate it with respect to the phi component. So this value is substituted in the above equation and we obtain the integration as shown over here. Now here what happens is we have complex integration which is present because of this parameter. So sine is involved with beta a, it is phi component and theta component. So such kind of integrations when we are having, we can use the Bessel function. We can use the Bessel function, in which Bessel function is given as what? J1, that is, this is the first order Bessel function. J1 and parameters are what? Parameters are given over here. So parameter is beta times a into sine theta and J1 is given by this entire condition. It is given by this equation. So what we do is we make use of this equation and we represent the vector retarded potential, which is a phi is equal to j times mu into the retarded current I divided by 2 pi r integration of this entire parameter. So when we substitute this over here, we get equation 9, which is represented over here. So here J1 of beta a sine theta is the Bessel function of the first order and whose argument is given by beta a sine theta. So now in previous this thing we had observed that E phi is equal to minus j omega a phi. So we obtained what is the value of a phi. Now we consider this. Now we consider a phi and substitute it in this equation to obtain what is the phi component of the electric field. So when we substitute this, we obtain E phi equal to, so if we consider that mu is equal to mu naught and we make beta omega as beta by c, because we see that beta is equal to omega by c, therefore omega can be replaced with beta into c, where beta is 2 pi by lambda into c. If I substitute this over here, then what happens is we can still simplify the equation and we obtain E phi, which is given by 60 pi beta a into I, that is the retarded current, divided by r into the Bessel function, first order Bessel function with the parameter which is beta a sine theta. Now from this we can obtain what is h theta. H theta is E phi divided by 120 pi. So when we substitute that equation, that is E phi over here, we obtain equation 60. So these are the two field values what we'll be looking forward for the loops in general case. These are the two field values. So in order to obtain the field, this is the parameter what we are looking. So we need to obtain the equation for vector retarded potential in the phi direction. So for that, again, we refer to the entire system and refer to this equation and obtain the result. So next part, what we'll be looking forward is identifying the radiation resistance, one for the small loop and the other one for the large loop. Now there are two conditions under which we can classify the loops. So one point what I had discussed was 1 by c by lambda. If this is less than 5, then I classify it as a small loop. I classify it as a small loop. Or else we can look for this condition also, that is when the area of the loop is less than lambda square by 100. If this condition is there, then we consider the loop to be small loop. So these are the two conditions based on which either of the condition you can consider, based on which we can classify whether the loop is a small loop or a large loop. So now let us consider that A is less than lambda square by 100. So if this is the case, we had seen that for small loop, what are the fields which are associated? What are the fields which are associated? That is, we observe the field parameters over here. So in this case, so these are the fields which are associated with the small loop. And in this case, right, loop in general case. So this can be, these equations will be utilized for identifying the radiation resistance of the large loops. So this is a general case. So we'll be using this in the large loops. So when we consider the field component, right, we have H theta, which is given by pi into I naught sine theta divided by R into A by lambda square. So this was actually the retarded potential. Now, since you have taken the magnitude, right, so if we just observe over here, what we have is, this is the retarded current. And it is given by what? It is given by, say, I naught into e raised to j omega t minus r by c. When we take magnitude of this one, right, it will be equal to I naught into 1, because magnitude of this one is 1. So this we had discussed in the previous session. So this value is equal to I naught. So when I take magnitude of this one, it will be equal to pi into I naught sine theta divided by R into A by lambda square. So we are using the magnitude in the derivation. So now again, if I refer to the previous discussion, right, how do I obtain the radiation resistance of any antenna? First, we consider the Poynting vector, or what we call as power density, which is the power flow per unit area. So we obtain what is the power density. Then we obtain the total power radiated by the antenna under consideration by taking the power density into account. That is by applying the power theorem. So we obtain power due to the antenna, which is total power which is radiated by the antenna which is under consideration. So this is the first step. And next step, what we do is we consider the total power radiated as I RMS square into the radiation resistance parameter. So this also gives you the radiation, this also gives you the power which is being radiated by the antenna, which is having a radiation resistance of RR. And by analogy, what happens is these two equations should be equal. So therefore you equate these two and obtain the expression for radiation resistance. Now the same concept will be followed. But in order to obtain those parameters, we had seen that we require E and H components. So here we can observe. So what is the total power which is being radiated? So this is the power theorem. The total power, sometimes we represent it as W, sometimes we represent it as P. So these are just a few different notations what you can observe. So the total power radiated is given by the average Poynting vector, which was identified as SR in the previous cases what we had discussed. So which is given by average value, or sometimes we represent it as the RMS value. We consider the surface integral of the Poynting vector. So this one is equal to half of So in loops, what we have for the orientation, we have E phi component and H theta component. We have E phi component and H theta component. So this is E cross H, half of E cross H. So therefore, since we have for electric field, we have only E phi component. So it will be simplified to E phi cross H theta. This is actually complex conjugate. This is actually complex conjugate. So that part is missing over there. So when we simplify this, right, when we simplify the cross product, so we have E theta, magnitude of E theta, magnitude of H phi its complex into sine theta, and a normal vector which is normal to the direction of E theta and H phi. So when we consider this one, right, what happens is we represent this in either H phi form. So here what we have, E theta divided by H phi, which is equal to 120 pi. So therefore what we have, E theta is equal to 120 pi into H phi. So we substitute this over here. What we get is, we get it as 120 pi into magnitude of, a magnitude of H phi into magnitude of H phi, its complex conjugate. So therefore this one gets simplified as 120 pi into magnitude of H phi its square. It is pertaining to the previous discussion what we had. So based on that, so this should be a cross product here that is missing. So when we simplify that, we obtain, and referring to this equation, we obtain what is the equation for total power which is being radiated by the antenna in terms of the field components. So in this one, we can either represent it with H phi or represent it with H theta or E phi. So that is what we have done over here. Now, based on the previous equation, what is the magnitude of H phi? Magnitude of H phi is given by pi into I naught sine theta divided by R into A by lambda square. So now, referring to this equation and substituting equation 1 in the total power, that is, I substituted it over here. So when I substitute it over here, what happens is, we will be simplifying this entire equation. So when I substitute and try to simplify the integration, what happens is, based on the simplification, we obtain the total power as 160 into pi raised to 4 I naught square into A by lambda square, the whole square. That is, I substituted H theta square, magnitude of H theta square in this equation, and H theta is obtained from equation 1. So when I substituted and simplified the integration, right, we end up with the total power which is being radiated by the antenna under consideration, which is given by equation 9. Now what we do is, we consider the same this thing with respect to radiation resistance. The total power radiated by the antenna is given by I RMS square into radiation resistance. But what is I RMS? I RMS is equal to peak value of the current divided by square root of 2. So when we substitute this, what happens is, we obtain WRMS, that is the total power which is being radiated, is equal to radiation resistance into I naught square divided by 2. Now what we do is, we equate equation 12 and equation 9. So this is the total power which is being radiated by the antenna under consideration. When you're considering the field, you obtain this equation. When you consider the radiation resistance, you get this equation. Now, since the antenna is same, these two equations have to be equal. Equation 9 and equation 12 have to be equal. So when you equate this, you obtain radiation resistance, which is given by 320 times pi raised to 4 into A by lambda square, the whole square. When you simplify, when you substitute the values and simplify it, it turns out to be nearly equal to 31,200 into A divided by lambda square divided by whole square. So this is the radiation resistance of the small loop. So here also they have done the same this thing. So here what they have done, they have specified, see, with the usual notations, prove that the radiation resistance of the small loop is 31,200 into A into N divided by lambda square, the whole square. So we can consider a small loop which is radiating in all directions. So with respect to this, the area of the loop is pi into A square, where A is the radius of the loop what we are considering. Circumference is 2 pi into A. And if RR is the radiation resistance of the antenna what you are considering, then what we have is the total power which is being radiated in terms of radiation resistance is given by this equation, wherein Im is nothing but the I naught what we have specified over there. So it is Im square divided by 2 into RR. Now next what we do is we make use of power theorem. So in which we have the total power which is radiated is equal to the surface integral of the pointing vector, average pointing vector what we are considering. So based on that, we obtain this part, that is, it is cross product of these two. So when you simplify this using the general equation, right, you end up with SR equal to this parameter. You simplify this parameter and you end up with this one. So when you substitute that in the power theorem, right, you get this equation, and when you simplify it still further by substituting H5, we obtain, so for small loop, right, we have to consider the previous equations what we have considered, what we have shown. So in this, what we have done is I have considered the H, theta and E5 components. You will get the same result. You'll get the same result. So here the simplification will be simple. So here they have considered the general case, and they have utilized it. So when they simplify this overall parameter, right, for small loop, you have to do all the simplifications when you are considering the general case. All the simplifications have to be considered. So then you will be obtaining it equal to what? After these all simplifications, you will be obtaining this equation. Okay. So this is what you will be having. So in this one, what we have done is we have just considered that the number of turns is equal to 1. So if you increase the number of turns, right, then what happens is area also will be like, if you just observe what we have. So if we have just one loop, right? So here n is equal to 1. The area of this one is A. If I have another loop, right, I'll have the total area as A plus A. There are two loops. So if I have another loop, that is the turn. So it will be like, so if there are n number of turns, that is total, there are n loops which are present. There are n loops. Then the total area will be n into A. So this is a minor change what you have to put in over here. That is over here we are discussing, right? In this one, you put it as n times A. So if I want the general condition, it will be n times A. Depending on if you have more number of loops in the same antenna, that will be identified with n. So in this one, you just replace A with n into A, which will give you the overall area of the loop. So it is like a spring. So you have something like this. This is actually a helical antenna. I'm just trying to give an analogy. So what is happening here? There is one turn, here there is another turn, next turn, so on. So even this is also a loop. This part is a loop structure. So I can try to see what will be the total area. So total area will be equal to n times A. So that is what we'll be considering. So if I just substitute that and continue with the same derivation, right, I'll be ending up with radiation resistance equal to 31,200 into n a into n divided by lambda square. Okay, sorry, I didn't see the typing. Okay, so this is the radiation resistance. So in this one, we can have the general condition wherein we can have n into a divided by lambda square, or it will be like a divided by lambda square, its whole square into n square. So that is one change what we have to incorporate. So this is all for today. Let us meet in the next session. Thank you.